If you have ever tried to stack 3 or 4 style LoRAs at once, you know the exact feeling of this loop. You guess a strength value, wait for the generation, and stare at an overcooked, muddy mess. The human brain scales poorly past 3 variables. Trying to balance 10 or 20 adapters destroys image coherence and forces hours of blind guessing. GimmBO swaps that wall of manual sliders for a different interaction, preferential choice. Finding the precise blend of 20 style adapters to lock in a consistent look for an entire project is a massive time sink. You're effectively searching in the dark. That search problem is exactly what won GimmBO a SIGGRAPH 2026 Best Paper Award. Instead of making you manipulate parameters, it asks you to rank a small batch of images based purely on your visual preference. It takes the bottleneck of trial and error out of your hands, shifting the workload entirely over to your GPU. GimmBO operates as deployable software today. The official research code is already built directly around a ComfyUI inference backend. Your interaction happens in a fast API browser server. The system does the complex math in the background, and your only job is to look at the generated images and click the ones you like best. But offloading that math means taking on a serious compute load. The default workflow generates a heavy batch of 8 candidate images for every single round of choices. If you are running a card with 24 gigabytes of VRAM or more, you can handle this smoothly. If you are on a lower VRAM card, you will need to apply explicit workarounds and accept longer wait times. Setting up a dedicated local server to crank through these batches is the entry price. But for a professional, it is the cost of doing business to escape manual guesswork. Giving a user 20 sliders is dangerous. It instantly explodes the search space into billions of mathematically useless combinations. The researchers mined 20,000 real user generations from Civitai to find a pattern. They discovered that successful, coherent merges almost always share a very low total combined adapter strength. This 3D unit cube represents every possible combination. The sliced corner, the B-capped simplex, keeps total adapter strength under a strict budget. By killing the gray area, it prevents overpowering the LoRAs. At 30 dimensions, this valid wedge collapses to a fraction of a percent. Naively dragging sliders means you spend almost all your time lost in the dead space. By forcing the search strictly inside the wedge, the system saves you from generating muddy images an expert wouldn't even try. The trade-off for staying in that safe zone is giving up microcontrol. You just provide a top 5 visual ranking of the generated batch. Those simple human choices feed into an engine called Preferential Bayesian Optimization. This contour map translates your taste into math. Every ranking drops a blue dot, building a dynamic landscape of your preferences. The algorithm uses an acquisition function to navigate this map, deciding which coefficient values to test in the next pink star batch. It constantly weighs 2 options: exploiting a spot it already knows you like, or probing a dark area of the map to see if something better is hiding there. You trade the illusion of manual control for an algorithmic partner, ensuring every generation sharpens the profile of exactly what you want. Reaching a final output carries a heavy toll. A typical search takes roughly 20 rounds of 8 candidates. That equates to about 160 heavy SDXL inferences per session. Stage 1 spends 10 iterations strictly hunting inside the B-capped simplex to see which adapters matter. It locks in the few active adapters and discards the rest. Stage 2 opens the search space, exclusively polishing the decimal strengths of those remaining adapters. By separating the search into these 2 distinct stages, the pipeline systematically forces convergence on a perfect blend. It achieves a mathematical precision that human hands on 20 sliders cannot reach. There is still one major point of friction before you even begin. How do you pull the right 20 candidates out of the thousands of LoRAs sitting online? The researchers address this by integrating GimmBO with Stylus. You type a text prompt, and Stylus automatically retrieves a relevant batch of community adapters to feed directly into the optimization loop. For a filmmaker, the real value lies in saving that perfected mathematical vector as a permanent style recipe. By using an extension like SDEdit, you can take that exact locked-in recipe and apply it across entirely new control images. That massive upfront GPU cost is justified because you are building a reusable style Bible for an entire production sequence. We have to acknowledge the blunt reality here. Generating 160 SDXL images in a single sitting demands serious patience and heavy hardware. The optimal profile for this workflow is a professional ComfyUI user running 24 gigabytes of VRAM or more, like an RTX 4090 or A6000. On those cards, the default batch of 8 generates smoothly. This chart breaks down your hardware options. If you only have a 16 gigabyte card, you must use CLI flags to halve the batch size, which significantly extends your wait time. The time investment pays off. The system earned its SIGGRAPH Best Paper Award by rigorously proving this method against manual sliders across thousands of simulated user tests. GimmBO asks for heavy hardware and lengthy compute times, but if you want to pull consistent, multi-concept styles out of a massive adapter library, this is the definitive path to get there.